We usually think the secret to the future of AI is just brute force. Like, if you want better AI, you just build a bigger, smarter, more massive brain.
Right, yeah. Just a single giant foundation model that knows literally everything about everything.
Exactly. But what if that whole assumption is, I don't know, entirely backwards? What if the secret to the next generation of artificial intelligence isn't about building a bigger brain at all, but actually about building a smarter manager?
It is a massive paradigm shift, honestly. We're really moving away from this fantasy of relying on a solitary genius to do all our work.
Yeah.
And we're moving toward orchestrating a highly coordinated team of specialists.
And that shift is exactly what we are focusing on today for you. We're looking at a state-of-the-art paper by Token Rhythm Technologies covering their Open School project,
Right, and it explores this really wild concept called harness native agentic routing.
which is quite a mouthful. But our mission for you today in this deep dive is to decode how shifting from a single AI model to a dynamically routed team of specialized models doesn't just, slash compute costs by like 90%.
Yeah, the savings are incredible.
But it actually creates this revolutionary data flywheel that might change how all future AI is trained. Okay, let's unpack this. To understand why we even need this smarter manager in the first place, we really have to look at how AI agents have fundamentally changed.
That is the perfect starting point, actually, because if you look at the old formula for an AI agent, it was remarkably simple. I mean, the equation was basically just agent equals model plus harness.
So you just picked one massive, expensive foundation model.
Yeah, say Claude Opus 4.8, and you just built a harness around it.
But for someone who, might just use AI casually, what exactly do we mean by a harness in this context?
Well, think of the harness as the software execution system. It's kind of like the administrative assistant to the brain. It manages the prompt context, it observes the digital environment, it holds the memory, it operates the tools.
Like a web search or a calculator.
Exactly. And it runs the verification loops to check the work. But in the old model, every single time that harness needed to think or make a decision, it called that exact same massive foundation model.
So it's just one giant brain doing every single little chore.
Precisely the problem. The landscape has completely shifted under our feet now. Today, models are structurally specialized. You have models that are absolute geniuses at complex code editing,
Right.
or recovering a tiny fact from a massive 1,000-page document. But those same genius models might be incredibly slow and wildly expensive if you just need them to format a simple tool call.
Or execute like basic if-then control logic.
Exactly. So the new formula is agent equals base models, plural, plus harness. They complement each other. By pooling them together, it creates what economists call a Pareto frontier across quality, latency, cost, and safety.
You threw out Pareto frontier there. For anyone who didn't major in economics, what does that actually look like in this scenario?
Well, imagine a graph representing trade-offs. You have speed on one axis, quality on another, and cost on a third.
Okay.
The Pareto frontier is that absolute perfect edge where you literally cannot make the system any faster without sacrificing quality, or make it smarter without jacking up the cost.
Right.
So by having a pool of specialized models instead of one giant one, OpenSquilla pushes that entire frontier outward. You basically get the best of all worlds.
I mean, it's like trying to build a construction crew where every single worker is a master architect with a PhD in structural engineering.
Yeah, that would be a nightmare.
Right. I mean, sure, they can build the house, but it's going to be astronomically expensive. And frankly, you don't need a master architect to swing every hammer or like carry bags of cement.
No, absolutely not.
You want the architect designing the blueprints, and you want affordable, specialized carpenters and laborers executing the actual physical steps. But let me push back on this a little bit.
Sir.
Isn't just switching between models based on the task a serving trick we already use? Like, if I use a premium chat interface today, there's often an auto-router.
Right? Yeah.
It says my hard math questions to a big model and my easy formatting questions to a fast model. Is this really all that new?
That is the trap a lot of developers fall into, assuming it is the exact same mechanism. What you are describing is per-query routing for a chat window. You ask a question, the router looks at the text of your prompt, picks a model, generates an answer, and the transaction is over.
Just a one-and-done thing.
Exactly. But an AI agent doesn't operate in single turns like a trivia game. An agent is on a mission. Its harness is multi-step. It is highly stateful, meaning it actually remembers what happened 5 steps ago, and it has to constantly recover from its own errors.
Because it's doing a whole job. It's actively navigating an environment.
Yes. Consider the downstream consequences here. If you make a seemingly clever, cheap routing decision at step 2 of a complex task, and that cheap model slightly messes up the formatting of a database query.
Oh.
Right. It might force your system to spend 10 times the original savings just doing error correction and context reconstruction way down at step 8.
Wow.
So model selection inside an agent isn't a simple chat serving trick. It is a really complex joint systems problem. The choice of model impacts the entire trajectory of the task.
That makes a ton of sense.
Yeah.
Because an agent operates in these complex, multi-step environments, we can't just route queries at the start line and, hope for the best. We have to route dynamically at every single step of the race.
Exactly.
And that brings us to the actual solution Token Rhythm introduces, which is harness-native agentic routing.
Yeah, that is the core innovation here. It is step-level model selection, but crucially, it is conditioned on the full harness state.
So not just a prompt.
Right, the router doesn't just look at the user's initial prompt. It looks at the context pressure, literally how full the system's memory is at that moment. It looks at the tool history. Like, have we tried this API call and failed twice already? It looks at recent verifier results and recovery status. It takes the entire current reality of the execution into account before picking the best worker for the very next step.
Been reading through the paper, it looks like you, the user, can actually choose how you want this manager to behave. There are 2 different regimes or modes. I saw one called cost-effective mode and another called high-accuracy mode.
Yes, exactly.
How does the system actually execute those?
So in cost-effective mode, which they call singleton routing, the router evaluates the pool of available models and selects the single best fit model for that specific turn.
Just one worker.
Right. The goal is to find the absolute cheapest worker who is mathematically guaranteed to succeed at that exact moment, given the current state of the harness.
Okay, and the high-accuracy mode.
High-accuracy mode or multi-model ensemble is much more aggressive. For the hardest steps, the router doesn't just pick one model, it dynamically builds a bespoke team.
Oh, wow. So it's drafting a whole committee on the fly.
Indeed, it might deploy one model whose only job is to retrieve documents, a completely different, highly analytical model to synthesize that information, and a third, ultra-fast, small model to fact-check the citations.
That's wild.
And then it uses an aggregator to fuse all their outputs together. So you rely on cheap specialists for the easy steps, and you summon this elite task force for the critical bottlenecks.
To make this happen, OpenSquilla uses a 4-layer routing stack.
Okay.
And the very first layer really caught my eye. It starts with this open source, light GBM cold start ranker.
Right, yeah.
Which sounds incredibly dense, but from what I gather, it's basically acting like a bouncer at a nightclub, right?
That is a brilliant analogy. The ranker is a very lightweight, traditional machine learning algorithm. It just sits at the very front door.
Okay.
When a request comes in, it makes a snap judgment. If the request is utterly trivial, like a user just saying hello or asking for the date, the bouncer just sends it to the absolute cheapest model instantly.
Because why overthink it?
Exactly. You don't want to waste expensive computational time thinking about how to route a task that requires zero thought.
Right. You don't call the architect to ask what time it is. But wait, I have a strategic question about this whole multi-step routing thing.
Sure.
If the harness is performing 20 or 30 steps, wouldn't picking a cheap model for an early step be incredibly risky?
Yeah.
Like, what if a small model hallucinates a tiny detail, the system doesn't catch it immediately, and that one bad ingredient just totally ruins the entire downstream recipe?
What's fascinating here is how the routing architecture mathematically handles that exact fear. Token Rhythm introduces this concept of trajectory-level loss.
Trajectory-level loss, okay.
Right, so the router isn't just looking at the immediate monetary cost of the next step. It is mathematically pricing in the residual risk and the downstream recovery costs.
So it's actively looking ahead. It's anticipating the domino effect.
It has to. A model is not actually cheap if its tiny failure triggers a massive system-wide context reconstruction later on. Let's say the harness state shows that the current step is highly ambiguous, or that an error here will be irreversible, like deleting a system file or sending an email to a client. The router's risk pricing mechanism flags that immediately.
It knows the stakes are high.
Yes, it realizes the capability demand is high, not necessarily because the task is intellectually complex, but because the penalty for failure is so severe. In those moments, it automatically escalates to a strong foundation model.
Okay.
It only trusts the cheap models when the trajectory level risk is low, or when an error can be instantly and cheaply verified.
Okay, it's one thing to theoretically match capabilities to tasks and talk about pricing in risk like an insurance actuary, but how does this actually perform when the rubber hits the road? Because the paper has some serious benchmark data, and the numbers are honestly a bit staggering.
They really are.
Let's talk about short tasks first. They used PinchBench, which tests short-horizon agent workflows. The baseline they used was an open claw harness running Opus 4.8 as its single massive brain.
Right, the traditional setup.
Exactly. And that baseline scored just over a 93, and it cost about 22 cents per task. Then they ran the exact same tasks using the open schooler routed agent. It scored practically the same, still over 93. Statistically indistinguishable quality,
Right.
but the cost.
Yeah.
It dropped to exactly 2 cents per task.
The efficiency gains there are just enormous. I mean, you are looking at an operation that is nearly an order of magnitude cheaper, roughly 11 times cheaper, while maintaining the exact same end-to-end quality.
It's mind-blowing. But then I looked at their results for Draco, which is a deep research benchmark. These are much longer, vastly more complex tasks that require reading through tons of documentation.
Very heavy workloads.
Yeah. And the routed policy preserved the top-tier quality again, and it still cut costs by a massive margin, about 43%. But I noticed a really surprising detail in the data tables. The routed run on Draco actually consumed more input tokens than the baseline.
Yes.
Wait, how do you cut your monetary costs almost in half while simultaneously burning through more compute tokens?
That seeming contradiction reveals the hidden mechanics of agentic routing perfectly. The cost savings do not come from just compressing the context or forcing the agent to read fewer documents. They come from a completely different price composition across the execution trajectory.
Price composition, meaning you are buying entirely different types of labor.
Spot on. Massive foundation models can cost upwards of $15 per million tokens just to process text. Smaller, highly optimized specialist models might cost literally pennies per million tokens.
Wow, okay.
On a deep research task, the agent has to read through massive amounts of raw documentation just to find the relevant pieces. If you use the old singleton approach, you are paying that premium $15 rate to have a genius model do basic reading comprehension and sorting.
It's like paying a senior law partner thousands of dollars an hour to highlight a phone book.
That captures it perfectly. With agentic routing, the harness assigns the heavy, high-token reading and sorting to the ultra-cheap specialist models.
Makes sense.
So it uses more tokens overall because the system might have the cheap model summarize things multiple times or cross-reference documents redundantly. But because that specific model is a fraction of the cost, the total monetary bill just plummets. You save the expensive senior law partner purely for the final, complex synthesis step.
Here's where it gets really interesting, because the paper doesn't just leave us with abstract benchmarks. It includes specific, real-world case studies to show what this looks like in practice.
Yeah, these are great.
Let's talk about the Mumbai Podcast Studio procurement case. The prompt was from a buyer who needed a 6-guest podcast setup delivered to Mumbai, India. The baseline, Opus 4.8 acting as a single brain, actually failed the live search.
Got overly cautious, right?
Yeah, it gave a generic list of microphones, warned the user they needed to verify all the local prices themselves, refused to estimate hardware failure rates, and scored a dismal 26 out of 100. It cost over 80 cents for that complete non-answer.
Well, it failed safely, avoiding hallucinations, but it still utterly failed the user's actual procurement need.
Right. But the OpenSquiller routed agent, specifically running in high accuracy mode, dynamically brought in a model called DeepSeek V4 Pro. And because of the way the harness managed the state and pulled in local context, the agent didn't just give generic advice.
It got incredibly specific.
First, it provided an India-specific street price matrix. Then, it pulled Windows 11 USB stability stats for the massive audio interfaces required for 6 guests. And crucially, it completely understood the environmental context and added a Mumbai monsoon checklist.
That was the best part.
It told the buyer, hey, you are in a highly humid environment, you absolutely need a dehumidifier, silica packs for the mic cases, and a voltage UPS to protect the gear from grid fluctuations. It raised the benchmark score to nearly 62, and get this, it slashed the cost from over 80 cents down to under 20 cents.
The mechanism there is beautiful. By offloading the generic search queries to a fast model, the router freed up the heavy reasoning model to actually analyze the geographical constraints.
Yeah.
You are getting a vastly superior, context-aware artifact for a fraction of the cost.
And there was another one that stood out. The CNC machining case. The prompt asked for precision machinery recommendations for aerospace parts using a very specific titanium alloy, Ti6Al4V.
Right.
The OPA's baseline totally missed the tooling specifics, but the routed model brought in a specialist that recognized the metallurgical constraints. It knew that standard ceramic tooling actually fails in titanium due to chemical reactivity and thermal shock.
Right.
It completely changed the recommendation, dramatically improving the engineering answer, again, for less money.
We also shouldn't overlook the multi-model ensemble successes, where the router dynamically builds that bespoke team we discussed earlier. There's the fascinating case study in the paper regarding coffee traceability for smallholder farmers.
Right, the ledger issue?
Yes. The baseline singleton models kept confusing certification ledgers like a platform called Fairtrace with actual field-level farm management apps. They basically lumped them all into one generic software recommendation.
So how did the routed ensemble fix that? Did it just happen to pick a smarter model?
No, it is entirely about how the models interacted. The router assigned a heavy synthesis model to draft the initial software recommendation, but simultaneously it ran a separate, specialized fact-checking model in parallel.
Oh, wow.
The synthesis model started to blur the lines between the apps, but the fact-checker flagged a contradiction in the live database regarding Fairtrace's compliance requirements. An aggregator model then took that conflict, realized Fairtrace is a mandatory supply chain ledger and not an offline field app, and forced the final output to separate the software into a two-tier architecture.
So the models essentially debated their way to a vastly improved recommendation.
Exactly.
Slashing costs by 90% on short tasks and massively upgrading the reasoning on deep tasks through these internal debates. That is incredible on its own. But the Token Rhythm paper argues that this cost control and accuracy boost is merely a byproduct. The real endgame of agentic routing is what it leaves behind.
Yes, and this is without a doubt the most vital concept in the entire paper, the data flywheel. Think about what happens every single time this router makes a decision. It naturally produces a highly structured data record.
Okay.
It logs the initial query, the exact state of the harness memory, the specific model the router chose, the full execution trace of what that model did next, the final outcome of the task, and the realized cost.
So it's not just logging, like the user asked X and the model answered Y. It's logging the entire internal thought process, the workflow, and the consequences.
Precisely.
So if we break down the mechanics of this flywheel for you, better routing means you use cheaper models. Cheaper models mean you have a much lower cost under a fixed budget.
Right.
Because it's cheaper, your agent harness can afford to execute way more tasks.
Right.
More tasks mean you collect millions more of these deeply detailed execution traces. And then here is the magic. You use those traces to train even better routers and to train new harness-native specialist models. You inject those new specialists back into your model pool, which makes your routing even more valuable, starting the cycle all over again, but faster.
It is a self-accelerating loop of capability and efficiency that just compounds over time.
But wait, I have a massive pushback on this.
Okay, let's hear it.
If a router is training its next generation on data produced by earlier, inherently dumber routers, doesn't it just learn to imitate its own mistakes? If the cold start bouncer picks the wrong model and you train your next AI on that log, aren't you just self-poisoning your own training data?
If we connect this to the bigger picture of how modern reinforcement learning works, we can see exactly why it avoids self-poisoning. In this specific schema, the router's choice of model is simply an action. Crucially, the router does not grade its own homework. The environment supplies the label.
The environment, meaning the verifiers, the code unit tests, whether the web search actually found the link.
Precisely the opposite of a self-fulfilling prophecy. Let's say a bad early-stage router picks a weak, cheap model for a really difficult coding step.
Okay.
The cheap model writes bad code and fails the unit test. The harness then has to spend $1 recovering from the error with a bigger model. That entire messy trace is logged, but it is logged as a negative example. The label essentially says, under this specific harness state, choosing this cheap model resulted in a failed verifier and a high recovery cost.
So it's not reading a transcript of a mistake and trying to blindly copy it. It's reading a log of consequences.
Exactly. It is logged feedback for what we call off-policy learning. Think of it like a sports team watching game tape. You don't watch a fumble to learn how to fumble. You watch it to analyze what specific defensive setup caused the fumble so you can avoid it next time. The next generation of the router looks at that trace and learns, okay, when I see context pressure this high, I do not pick the cheap model because I can clearly see the historical cost of that mistake. The bad decisions of the early router are actually some of the most valuable training data you can possibly generate because they perfectly map the boundaries of where cheap models fail.
That is absolutely brilliant. It learns from the bruises without having to feel the pain in live production twice. Which brings us to the ultimate vision presented by Token Rhythm Technologies, the end state of this whole ecosystem. Based on this flywheel, they predict the industry is moving toward a three-layer model pool.
Right, a highly stratified system.
Layer 1 is your general foundation models of massive, expensive brains. You kick them around, but only for long-tail, highly ambiguous, high-stakes tasks. Layer 2 is harness-native specialist models. These are the models trained directly from the execution traces we just talked about, perfectly adapted to your specific tools and workflows.
And layer 3 is ultra-cheap fast paths, tiny models, simple classifiers, used just for routine control logic and moving data around.
And this three-layer end state carries a massive industry implication. Think about the nature of this harness-native routing data. It is incredibly hard to crawl and almost impossible to buy.
Why is that?
If you are building AI today, you can scrape the public web for a final answer. You can scrape Wikipedia or Reddit or news sites, but you cannot scrape the sequence of harness states, the rejected model alternatives, the context compression decisions, and the tool errors that led to a successful agent outcome.
Because all of that invisible work happens behind closed doors, deep inside the server's runtime memory. It never actually touches the public internet.
Which means the old playbook of just scraping more data is obsolete. The harness is no longer just a wrapper you put around a model to make it usable. The harness has become the environment breeding the next generation of models. The company that operates the best harness at scale will generate proprietary training data that a web scraping competitor simply cannot replicate. So what does this all mean for you? Well, consider this. We started today by talking about how the obsession in the AI industry has been singular, building a bigger brain. But if the most valuable, highest signal training data for the future of artificial intelligence is no longer found on the public internet.
Which is wild to think about.
Yeah, if it is instead generated and hidden deep inside these dynamic, routed execution traces, what happens to the balance of power in the tech world? Will the ultimate winner in AI really be the company that scraped the most websites to build the biggest foundation model? Or will it be the company that ran the most efficient agent harnesses, silently harvesting the invisible data of how work actually gets done? The massive brain gets all the magazine covers and the glory, but it just might be the manager that inherits the earth. Thank you for joining us on this deep dive.